One has to familiarize oneself with a couple of concepts, mathematical concepts, in order to unpack some of the mathematics in Roshni Rashid's paper. The first idea is that of a factorial, and that's written as n with an exclamation mark like that. And it's defined as the following. It's n itself times n minus 1 times n minus 2 all the way into 3 times 2 times 1. And that's just the definition of n factorial. Let's see what 4 factorial might be. That would be 4 times 4 minus 1 times 4 minus 2, etc., all the way to 1. So that's 4 times 3 times 2, actually times 1. So this is 2 and the next number is 1. You don't need a dot, dot, dot here. Right? So that's 4 factorial, and that is 24. Similarly, 5 factorial would be the following. It would be 5 times 4 times 3 times 2 times 1. So it's 1 less than the original number, which is 5. That's the next number, 4. And 1 less than that is 3. And 1 less than that is 2. And 1 less than that is 1. So the concept of factorial arises everywhere, in many places in mathematics, particularly in combinatorics. And some of what shows up in this paper is related to the factorial. And the second idea, of course, is the combinatorial concept of n choose k, which means n, sometimes written as n choose k, and this means it's a way to choose k objects from n objects, right? And that is defined as the following. It's defined in terms of factorial. So it's defined as n factorial divided by k factorial times n minus k factorial. So it looks a bit involved, and you say, well, it's a bit of a complicated formula if you just want to find a way to choose k objects from n objects. But intuitively you can think, what if n is 4 and k is 2? How would you do that? So how do you choose 2 objects out of 4 objects? One easy example would be to just think of the numbers in this set, 1, 2, 3, 4. How many ways can you choose 2 of these numbers from 4 numbers? The first idea is to the first concept would be to visit what n factorial might be, where n is 4. That means how do you make combinations out of these 4 objects? How many combinations can you make? That would be 4 factorial combinations. Why? For instance, you can see one combination would just be 1, 2, 3, 4. Another combination would be, if you keep 1 in its original place and you switch 2 and 3, you'd have 3, 2, 4. So you'd have 1 in its place. The next number would be 3 and 2, and then 4. Another way would be to place 1 where it is and maybe 2 where it is and switch 3 and 4 together. So 4, 3. So 1, 2, 4, 3 is another combination. 1, 3, 4, 2 is another combination. And then 1, 4, 2, 3 is another combination. And 1, 4, 3, 2 is another combination. So you can see 6 combinations by just keeping 1 in its place. And if you do that to each of the numbers, you can see that there'll be 4 times 6, which is 24, right? So there'll be 24 combinations of 1, 2, 3, 4, and its different ways of writing it. So that's one idea. But we were saying, how do we choose any two of these items? Well, you can sort of see logically, if we were choosing 4 out of 4, we were choosing 2 objects out of 4 objects. The formula says it's n factorial divided by k factorial times n minus k factorial, correct? So that is 4 factorial divided by, what is k? K is 2. So it's divided by 2 factorial times n minus k, which is 4 minus 2, which is 4 minus 2 is 2 factorial. So that's 4 factorial divided by 2 factorial times 2 factorial. So 4 factorial is the number of combinations of any of these 4 objects, right? Of these 4 objects. But if you choose 2, you have to divide by 2. And there are 2 ways of choosing those 2. So you can say, I choose 1, 2, but there are 2 ways of choosing 1, 2. So it's either 1, 2 or 2, 1. So you're choosing 2 objects, and there's 2 ways of choosing those 2 objects. So you get 4 factorial divided by 2 factorial times 2 factorial, which is 24, divided by 2 factorial is nearly 2 times 1, so that's 2. So it's 24 divided by 2 times 2, which is 6. So there are 6 different ways in which you can choose 2 of these numbers out of these 4 numbers. So intuitively you can see why the formula of n choose k works. Alright? So that's the second concept. Now this concept is quite fundamental to the binomial theorem, which shows up everywhere. And it's a very important theorem in combinatorics. And Sufi and Al-Halabi, they talk about the binomial theorem. And Rajvi's paper also talks about this. So the third concept is that of the binomial theorem. Now, in order to understand the binomial theorem, we first visit just a simple idea, a simple concept that we saw in school, and that is raising to the power of a binomial term. So a term with, say, 2 objects in it. So you have 2 variables, x and y, raised to a power. When it's raised to the power 0, that by definition is 1. There's a proof, but that's a bit involved, so we'll just leave it at that. X plus y raised to 1 is just x plus y. X plus y raised to 2 is x plus y times x plus y. And you can work this out, so that's x times x, which is x squared, plus x times y, that's xy, but you have to add yx as well, that's y times x. So x times y plus y times x is 2xy, because y times x is the same as x times y. And you need to add the final term, which is y squared. What is meant by the coefficient of any of these terms is the number that lies before the alphabet. So it's 1x plus 1y, for instance, 1x squared plus 2xy plus 1y squared. Yeah? And if you expand out x plus y whole cubed, I leave it as an exercise for you to see that that would be x cubed plus 3x squared y plus 3xy squared plus y cubed. Alright? And the coefficients are 1, 3, 3, and 1 again. So you might notice that very conveniently and rather magically, this forms a pyramidical structure that is called the Pascal triangle. If I just write the coefficient of every term here, I have 1 for the first term, I have 1 and 1 for the second, and I have 1, 2, 1 for the third, And for the fourth, I have 1, 3, 3, 1. So 1, 3, 3, 1. If you notice, this goes on to form a very neat triangle. This is called Pascal's triangle. And strangely enough, it's related to the number 11. So the first number is 11 to the 0. The second is 11. 11 squared is 121. 11 cubed is 1331, and so on and so forth. But it breaks down after a point, and it's a good exercise to think why that might be so. So why am I doing all this? This binomial term, this x plus y raised to some number, is written as the following. If n is any integer number, it can also be negative, but we'll talk about positive numbers here. So x plus y raised to n is actually written as a formula called the binomial formula. And we visit the binomial formula in Rashdi's paper quite a few times. In fact, if you write it in the way that he presents it, it's nothing, it's written in the paper as the following. It's nothing but k goes from 0 to n choose k, and x to the n minus k times y raised to k. It's just the expansion of this term to the right. It might look a bit sophisticated, but all it means is that the sigma, what does this mean? This just means summation. And you may have seen this at O-level or various other stages, even earlier in school. N choose k, which is this, we've discussed before. That's just n factorial divided by k factorial times n minus k factorial. And this is merely a number. It's not a matrix. That you have to remember. So it's just this number, and its formula is n factorial divided by k factorial times n minus k factorial. So what does the term above mean? It just means that I've got to sum over from k is equal to 0 all the way to n the following. I have to sum over what happens when k is equal to 0, right? And n can be any number. It can be 10, for example. So k is equal to 0 all the way to n of x to the n minus 0 y to the 0. So my first term would be when k is equal to 0. And I add to that, and I say what happens when k is equal to 1. And I can just replace the n that I'm thinking of. N can be any number, as long as it's not problematic. It can even go up to infinity. So it goes n choose 1 times x to the n minus 1, because k is 1, y to the 1, plus dot 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 all the way to n choose n, that's my last term, x to the n minus n, because k has marched all the way to n, right? And what is n minus n? That's just 0. X raised to 0 is just 1. Similarly, n choose n, how do you choose n objects from n things from n things? That's one way, so that should be 1 as well. And y to the k becomes n now. So your final term is y to the n. So you just replace n with the number of terms that you want to expand to. And you'll get one extra term always than n in the total number of terms. Okay, that's your binomial expansion. So Al-Tusi and Al-Halabi and Ibn Sina, they do mention the binomial theorem several times. So now in the next video, we'll talk about the specifics of the paper. We've got our 3 concepts lined up, and in the next video, we'll talk about it.